So this is my Stat 512 project. My topic is to find the association of air pollution levels with traffic and meteorological variables using linear regression methods. So first the introduction. So my goal is to explore associations, that is, gain some insight about the factors that are affecting the pollution level. This has obviously great moral interests and academic ones. We also want to explore the predictive capabilities that we can leverage through our linear regression model. This is important as we can use to regulate the factors which might increase the air pollution level and so on. So our response variable would be the nitrite level in air, the NO2. So it is indicator of air quality and pollution level, and we want to use several meteorological variables such as temperatures, wind speed, etc. as explanatory variable. So this is an exploratory analysis, and we want to find some associations, some useful associations that we can leverage. So uh, the data file has been gathered from the Carnegie Mellon statlib database. So the link is as follows, and the description of the data can be found as well. So basically, it's a 500 observation sample with different with recorded NO2 values and several variables corresponding to the traffic, meteorological measurements, and hour of the day. So this was published by the Norwegian Public Roads Administration, and so let's look at these specific research questions. So first we'll start out with seeing whether there is any significant linear relationship between the explanatory and the response variable in the first place. So this would be our model. This is a linear model with response y and xi's as the explanatory, and our null is the whether all of the coefficients are zero, or at least one of them is not zero. This is the general global test. Then secondly, we will like to see, is there any significant interaction terms explaining the response. So this is actually a relevant question, as many of the meteorological variables show something called the emerging effect. So they won't have that much impact individually, but together they might have an interaction effect. For example, like the temperature and temperature with its interaction with time throughout the day can show significant effects. So in that case, our model would be a response equal to the general first order terms and then the interaction terms, and we want to see whether the quotient of the interaction terms are all zero, or at least one of them is non-zero. So then after doing this exploratory analysis, we want to see which one of them are significant. Can we drop any of these variables? And we want to develop a theoretical relationship which we can use to study. As I said, it's an exploratory analysis, so that is a matter of interest. So we want to find the best subset of predictors, and then finally our most important goal would be to find a efficient predictive model based on these best subset, for which we'll look at advanced remedial methods such as the ridge or robust regression. For all of our analysis, we will use the tenfold cross validation as our metric to evaluate the prediction performance. Okay, so let's start. So this is what our data looks like. So the in the original data set, there is an extra column saying the number of day, which is basically just an id variable, so I drop it. So the variables of interest left are this NO2 variable, which is just the log concentration of the NO2 levels in air. This will be a response variable. The traffic variable is just the log of the number of cars per hour. G temp is basically the ground temperature above 2 meters above the ground. Wind is the wind speed in meter per seconds. Temperature difference is just the temperature difference between 25 and 2 meters above the ground. Wind direction is the wind direction in degrees from 0 to 360. R is just the hour of the day. Our total sample size is 500 observations. So for starters, we plot a correlation. We compute the correlation matrix between the variables, and we see that the NO2 response variable has moderate and decent amount of correlations with the explanatory variables, which is a good sign. Correlation is a sign of some sort of strength of a linear relationship. Uh, and also one more thing to notice is that the traffic and R variable has almost like 57% correlation, which might cause trouble. We'll see, but that's the first thing we notice. So yeah, our first model, we fitted the basic first order model, which looks like this, and the global F test is rejected at 99.9% level. So that is telling us that there is definitely some variables which are important. The explaining the linear relationship with NO2. So these are the R square and the adjusted R square. So we also can see the t values. So the t values and their corresponding p values, all of them are like significant at the 99.9% except the wind direction variable. So this is a pretty good start. And then we look at the variation inflation factor, which is less than 10. So that is also good. So this was our first order model. Let's look at the diagnostics. So the residual plots look fine. I don't see any patterns. um, it's centered around 0. There are these few points which have high leverage and high cook. These are the outliers somewhat, which influence the model. We'll see how we deal with them. And for the normal QQ plot, most of the points are along the diagonal, which is good, but you see these tails which deviate a lot from the diagonal, which will indeed uh, fail, like which will make the Shapiro test fail, as it is really sensitive. It's a really sensitive test, so that's not a surprise. But in long term, this shouldn't be much of a problem. But we'll see later on when we deal with advanced remedial methods how we um, address them. So next thing is we assume linear relationship with all of these explanatory variables, but we want to see whether it makes sense actually. So is the relationship with all of these explanatory variable and NO2 actually linear? So what we do, we perform a lack of fit test based on each explanatory variable. So lack of test each explanatory variable xi. So the reduced model will be just the simple linear regression with NO2, and the full model would be the averages of y value at a particular x. And so we find out that all of the variables are good. They don't show any lack of fit, except the R variable, wind direction, temperature difference, and the wind speed, which show a lack of fit at 0.05 level, 95%. So we look at the plots, and so this plot here represents we have the scatter plot in the background between NO2 and the explanatory variable, and the red points, the red dots represent the fitted values of the full model, in this case the averaged out y values, and the line represents the regression line, simple regression line. And we see that for the r variable, there is a non-linear, some kind of pattern, a bit periodic, goes up and down, so that's why there is a lack of fit. So we need to address that there is a non-linear relationship happening. For wind, the lack of test, wind direction, the lack of fit test fails because, as you can see, there are so many red points, as many as the real points scattered all around. So there's not many replicates for the lack of test to actually function well. So that's why it fails. So we don't mind that much. We know why it fails. For uh, the temperature difference variable, it looks fine in the center and the line passes through the mean, it's close to the mean red points, but due to these extreme values, where there are not many replicates, it skews the result of lack of fit. So again, as for temperature difference, we won't rely on the showing lack of fit. And again, for the wind variable, we actually see that there is a nonlinear pattern. So it starts off high and then it's decays slowly. It's not actually linear. So we might need some transformations for the hour and the wind. So for the wind variable, I perform a log transformation, and we'll see that it actually fixes this issue. And for the R variable, though, I can't find any non-trivial functional transformation which would fix this. I tried various polynomials, but the issue still persists. So yeah, I couldn't fix that. But the wind variable we fixed, and it performed better, as we'll see. So the next model is the transformation after we perform after we perform the log transformation to the wind variable. So this is the transform model, and then if we see the same plot, now we see that the averaged out y values, the red points, lie very close to the actual regression line fitting. So here is the lack of fit ANOVA table, which says that which we can't reject anymore, so there is no lack of fit anymore. And the r square actually also increases. The r square of the model increases from 0.5076 to 0.59, which is good. Even the adjusted r square increases a bit because we are using the same amount of predictors. So yeah, the VIF is again less than 10, and the other residuals, plots and diagnostics, remains the same. So moving on, next we move on to seeing that, okay, now we are sure like the linear relationships are good to go, we don't need polynomials. But what about the interaction terms? Are the interaction terms significant, or they help us explain more variation in the NO2 variable? So this will be our model with the interaction terms, and our null hypothesis would be like, are any of the coefficients of these interaction terms zero, or at least one of them is non-zero. So in total, including the intercept and 15 interaction terms, there are 22 variables, and we use the general linear test to test this hypothesis again. So the reduced model is our previous model, model 2, with the transformed wind variable first order model, and the full model is model 3, this model with interaction terms. And we here see the ANOVA table. We reject the GLT at 99% significance, which is really good. So that means there is definitely like some, the interaction terms have influence. So so that's a good step, but the thing is, we have a lot of variables now. We know it's significant, but we would like to know which of them are actually which of the interactions are actually important. So next step would be our model selection procedure. We would use best subset selection to reduce this model tree into something to have only those terms which are significant. So next we perform the best subset algorithm on the previous model, model 3, which had total 22 variables including 15 interaction terms. And I run the code and stuff. I haven't included all of the tables because it's too much for PPT, but if you can see it in the RMD PDF provided with the project. So here is below here is the summary. So these are the various criterias for measuring the best subset. First is the sum of squares, R square, HST, malus CP, EIC, SPC, BIC, press P. So, and the first column is first row represents the minimum, the p values, the amount of the number of predictors for which its corresponding model minimizes this criterion in the column mentioned in the column. And the second row is the similar thing, but the value of p corresponding to their model which maximizes these criteria. So we see that the sum of square errors is minimized at the full model with all the predictors, which is no surprise because we are not penalizing the predictors. And for the R square, similarly, the maximum is with all predictors, it's maximized. R square adjusted though is maximized at 14. Malus CP is minimized at 14 again. AIC 14. BIC is a bit sensitive, so it penalizes a bit more. So its optimum value is at 10, and press P at 13. So it looks like having a view at this table that the model with P equal to 14 predictors is the including the intercept is the optimal choice. So as I mentioned in the research question though, that our one of our main goals is prediction. So one might say, oh, but we should choose the 13 the model with 13 predicted too, we can't disregard it. So I compared the p equal to 14 and 13. Actually the press p values are almost the same, and the difference is only in the third decimal place. And also for like satisfaction, I ran a tenfold cross validation between this p equal to 13 and p equal to 14 model, and the p equal to 14 actually performs better in terms of the root mean square error metric. So with all that considered, so 1 2 3 4, basically 4 of the criterions prefer the p equal to 14 model, and that's what we use and proceed with. So the p equal to 14 model, which variables does it include actually? So I extract the variables which the best model comprises of, and these are the list of the variables. uh, so these variables, some of them are like the direct influence variables, and most of them are actually the interaction terms. So I have written it down in a like more readable way. So this two in red are response variable. These green terms are the direct influence. So only traffic, wind, temperature difference are the direct influence variables. The rest of those variables like wind direction, temperature difference, ground temperatures appear as interaction terms with these major variables, which makes sense. Like wind direction alone shouldn't tell you much about the air pollution levels, but wind along with wind direction, let's like this term should tell you like the should control the effect. Like direction alone doesn't mean much. So Yeah, similarly, ground temperature and wind, and a lot of these interaction terms can be interpreted. Details can be seen, the coefficient values and stuff can be seen in the document. For now, just this is our like best subset model. So now once we have our best subset model, uh, because prediction is a major focus, we would like to get rid of that outlier influences, those influential points, and make our predictions less variable. So the next thing that pops up in our mind is to run an advanced remedial measure, like something like robust regression, to reduce influence of outliers, make the predictions more stable. And also, as we have included some interaction terms, yeah, some people might be bothered about collinearity issues. There might be some overfitting due to interactions in terms of prediction. So we can use some regularization techniques such as ridge regression to introduce some bias but reduce the variance in predictability. So we'll compare these two advanced remedial measures applied on this final model 4. So uh, that's what we do in the next slide. So here are the results for the robust and rich regression on model 4. So all of these results are trained with the tenfold cross validation. So the models are chosen which reduces the root mean square error based on the tenfold cross validation. We use the cat package with the RLM and rich method for this. So first here we have the robust linear regression. So we see that we want the intercept. So look at these last three rows, and we have like for different like weights like the Huber, Hampel and Biosquare, we have these three RMSE and the corresponding averaged out R squared values. And we see that the robust regression with psi equal to like the weights equal to Hampel gives us the lowest RMSC, 0.5049, with tenfold cross validation. So this will be our choice, the Hampel one. And in contrast, when we look at the rich regression, we perform it with tenfold cross validation, and we find that for lambda equal to 0.0384, that's the optimum value. And then we find its MSC, it's around 0.268, which is equivalent of RMSC of 0.5176. So it's a bit higher than what we get for the robust regression with Hampel, but it's comparable to, it's not that far off, and it's comparable to Huber and Bask. But yeah, nonetheless, rich regression doesn't penalize, like doesn't offer much. So finally, when we compare all of these models, I have compiled this result in a table. So model 1 was our first order basic model. Model 2, the descriptions of each of these models are given. Our final models were model 4 on robust regression and rich, with robust and rich regression. And here are the tenfold cross validation RMSE and R square values. And we can see as we move along with each step of an analysis, our RMSE cross validation actually decreases. And we have somehow managed with the robust regression with the weights equal to Hampel, it's around 0.50, which is the minimum. And similarly, the R square increases from 0.48, we started cross validation R square 0.48 to 0.56, which is a huge improvement. And again, it's model 4 with the robust regression. So yeah, so this is basically summarizes this, these lines basically summarize the table. So we started out with our basic model, we improved our prediction power and R square in each step. We were able to get our final model 4, this model describing which primary factors and interaction factors explain variation of the response variables, which answers our research question of finding the association or the relationship which the like variables follow. significantly. So model 4 can be used for theoretical purposes and interpretation. The last two models with robust and rich are just different regression methods, but the underlying model is the same. And for uh, prediction, we can rely on the robust version of model 4. So the issues which were still unresolved were the normality issues. So because there are these few observations which are at the tail, which are extreme, they cause the Shapiro test to fail. But if we look at the QQ norm plot, it's almost along the diagonal. So for prediction purposes, this shouldn't be as much as a problem. And obviously, this was all linear model analysis. We can do better by implementing some nonlinear complex nonlinear models like neural nets and such to increase our prediction accuracy. But um, but I'm pretty satisfied with what we got with our linear regression simple model. R square of 56%, cross validation R square of 56%, which is pretty, it's not bad, it's decent for, yeah. So that's it. That was my presentation. Have a nice one.